Okay, before we get to reviewing the brain burner, shh, 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 before we get to review the brain burner from homework 11, which I want to do and I'm set up to do, I want to give you some news, some good, some bad, and some medium. So the bad news is not really that bad, but I didn't get the clicker stuff published in web courses. I thought I had published it last week. I already looked at it and stuff, but I didn't have time to do it um, and put it in web courses and activate it so you can see it. But I'll try to do that uh, this afternoon. And the reason I didn't do it in the past 3 days is because I was working like a maniac to get my astronomy midterm ready for 1:30 this afternoon. And it's ready, but I haven't uploaded that stuff. But it will. So that's the bad news. And it's only medium bad news. Now, the medium news, okay, that's the bad and the medium. Now, the good news is that it's who's it's Alex's birthday today. Go ahead and stand up. And happy birthday to you. Happy birthday to you. Happy birthday, mighty Alex. Happy birthday to you. Anybody else is your birthday today? Raise your hand if it's your birthday and you're not too embarrassed to say it. All right, anyways, it's Alex's birthday. Now, Alex, we have a special treat for you, just for you. Okay, and we'll be doing that in just a minute. Um, let's see. Okay, I already mentioned the clicking scores. Let's take a look at homework 11, brain burner. And it was a problem in which you were to compute from brain burner difficulty information the moment of inertia of an object connected by four or by two light rods of negligible mass at specific locations. Now, the variable that changed on every instance, every attempt, was the mass. But the positions were all the same. And so this is the overhead view of it in a 3D or pseudo 3D view of the overhead view of the locations. Here are the points TU, V, and W. And you may have noticed that they're threes and fours, pluses and minuses here and there, but either a 4 or a 3. And no 4 fours, no 3 threes. It's always a 3 and a 4 or a 4 and a 3. All right. Now there's a reason for that, which you may have noticed if you calculated this, and we'll get to that in a minute. Here's a perspective view, Courtney, of this array of point masses. Here it is. Okay, so this one now we're looking kind of in perspective, and I still have that cubical frame around it traced in. Let me remove that now. So there are the coordinate axes, and here are the four. Get my cursor over here. Here we go. Here are the four mass points. I didn't label them. I should have, I guess. I believe this is T down here, U here, V here, and W over here. At any rate, these are the, well, actually, you could tell. Okay, this is W here, this is V, this is U, and this one over here in the third quadrant, negative quadrant, is point T. All right. Now, and there's just to emphasize, go ahead and make a note, that's the feature or the value in the calculation that changed on every attempt. So you may have seen 4 different masses, but always these 3 set locations. And it wasn't any more difficult than the previous problem, but the previous problem, everything was set on one of the coordinate axes. So one of the coordinates was always 0 in the problem before this, and it was multiple choice. This was a calculation. So let's get down to it. The basic idea is to add up mr squared for each point mass, and so that's basically executing this formula. Now, just go ahead and write that down. That's a big capital Greek letter sigma, and in fancy mathematical terms, that means add up everything. Capital sigma for sum, S for sigma, S for sum. Add them up. So you add up mr squared for each pixel of mass, or in this case, for each point mass. You know, if you have a solid body, you know, you have to, you know, pixelate it up and, you know, count each pixel, mr squared for each one. And this one, we're going to do the same sort of philosophy to execute this thing, but we only have to do it 4 times. So my sum, this sum over all the pixels of the quantity mr squared for each pixel is just a sum of 4 numbers, or 4 subcalculations. Okay, so mr, and one more thing. If you do this on graph paper, the distance from the origin is always the hypotenuse, Gabby, of a 3 meter by 4 meter right triangle. All right, now the reason that that's nice is that the hypotenuse of a 3 by 4 meter triangle is always 5. And the square of that hypotenuse is 25. All right, so 9 plus 16, 3 squared plus 4 squared is 25. Now, we don't have to square root anything, Alex. It is your birthday, but we don't have to square root anything. All right? But we do have to calculate r squared for each of the point masses in it. And the way that I set it up, it's, you know, 5 squared for this point mass, distance, r squared from the axis. 5 squared, 5 square meters for this point mass away from the axis. For this one up here in the first quadrant, and for this one down here in the fourth quadrant. And so for each mr squared, you basically have, in this example anyways, 1.7 times 25 square meters. All right? Now, if we had a sphere or a stick, as I wrote about in the textbook, it's a little trickier, but you can, you know, you can still do it. It requires a little bit of trig is all. A rectangle, you know, a cube, a box that's not cubic. You know, this is a rectangular box, but the length is different from the height, and that's different from the depth. You can do that as well. About the center mass, it's not a problem. But for this one, it's pretty easy. Each of those babies is 42.5 kilogram meters squared. So the sum up here, add up mr squared for each point mass, is basically add up 42.5 Maria kilogram meters squared 4 times. Right? So that's kind of cinchy. I mean, and this is not the only way that you can do it. You know, I'm doing it up in this particular manner, but you might have done your algebra and still come up with a total moment of inertia of 170 kilogram meters squared, if that was your problem. Now, we're not going to specialize in computing moment of inertia. All right, we've done a couple basic ones, but this one I wanted to emphasize because it's going to help us understand the demonstrations. Okay, and we've got a bunch of demonstrations up here that we're going to do in just a minute. But before we do that, let me pause for questions. Do you have any questions about this particular calculation? Because I know there was some discussion about it and some a little bit of frustration. I won't use the word flailing. I'll just say there was a little bit of frustration. Okay, question. Yeah, this Pythagorean theorem right here. Yeah, you don't, because the stuff that you're adding up is not mr but mr squared. I mean, if you wanted to just know the distance, yeah, you'd have to take the square root. But we want to know the square of the distance and multiply by the mass and then add it all up. Okay, uh, so yeah, this time you don't have to square root anything. Okay, but like if I was to ask you, well, how far away is it from the origin? Then you'd have to square root it. But if you want r squared, just leave it as r squared. It's perfectly. And for moment of inertia, that's what you want, r squared. Another question. Got a lot of people absent today. Megan.
Will there be a question on any of our future tests or what have you, where the points aren't all the same distance away from the origin?
The question is, will there be a question or calculation on the next exam where all the points are not the same distance? And I could answer that question, Megan, but then I'd be telling you what's going to be on the exam. But if you savvy this one, you can savvy one where you have, a little bit of oblong stretch. It's, I'm not gonna force you to do like ultra trig and stuff like that. But a little bit fancier than this, yeah, you guys could probably handle if you savvy this one. And not to say that that's going to be on the test, but if it is on the test, you'll be set. Another question. By the way, another bit of kind of bad news, but it's only medium bad news. If you were not here Tuesday to get your exam printout, or if you were late and you had to leave early and didn't get your exam printout, I don't have the exam printouts today, but I'll have them next Tuesday. So we haven't forgotten about it. I'm just stripped down to the bare essentials today because I'm lugging around a big pile of tests for my astronomy students. Gabby?
Can you use the distance formula as well instead of the Pythagorean theorem?
The question was, can you use the distance formula instead of the Pythagorean theorem? And the answer to that is yes, no. Yeah, yes, no, because the distance formula is based on the Pythagorean theorem. Okay? Unless you're talking about the 4 dimensions of space-time, then it's slightly different. But that's the theory of relativity. But in this spatial distances, yep. The distance formula is based on the Pythagorean theorem. So, okay, now Melanie, we're going to do some demonstrations now, okay? And we're going to use, go ahead and jot down this formula. We've already talked about it. And we're going to be talking about not pixels, but elements of mass moving around to different locations. And Megan, we're going to change the location and thereby change the moment of inertia. And that's going to have an effect on the angular velocity, omega. Okay, so we want to know this formula. And here's an illustration from the text, the new textbook chapter. And here are the 3 different demonstrations that we're going to do. Now I'm going to keep this up on the screen. And now I need, Alex, I need 1 volunteer from the audience. I'm looking at you, Alex. Okay, do you want to come on up? Okay. Come on, mosey on up here. All right, now I need, and let me turn on the lights. Oops. No, the other way. Okay. Okay. Now I need 1 more volunteer from the audience. Who would like to volunteer? Anybody from the back row? The slackers in the back row. Ooh, I'm not supposed to say that. Sorry. The the illustrious students in the back row. Anybody? Come on up. Okay. Now what we're going to do, first we're going to do the ice skater effect. Okay. Okay. Now, let me just ask you a question. Boy, those are sleeves, right? Yeah.
Yeah, I guess so.
Okay, she's going to do the ice skater effect. What's your first name? Shalissa. Okay, and Alex. And you're going to do the bicycle wheel demonstration. Okay. Are you pretty strong?
I don't know.
You have to. It's your birthday. You have to be.
Okay.
Okay. Okay. So Shalissa, take a seat on this stool up front here. Okay. And Hector, go ahead and start recording. And what we're going to do with Shalissa is demonstrate the ice skater effect. And she's going to hold those. Shalissa, I want you to actually, can you move the stool a little bit further away from the table, Darian? Go ahead and stand up, Shalissa. You have to take the whole thing over. Yeah. That's better. Okay. All right. Now, Shalissa, Hector is recording this, so it'll be on YouTube. Is that all right? Okay. All right. Now, Shalissa, I want you to just hold those in your lap and let Darian spin you around a little bit. And this is just to show you, okay, that she's on a lab stool, and the lab stool is on a turntable with really good bearings. So did I tell you to stop?
She's dizzy.
Oh, and that's one of the things you got to be careful about. But it's good. It has really good bearings, so not a lot of friction. There's not a lot of friction, and that means not a lot of torque to counter her angular momentum state. Okay. Now she can change her inertia, her moment of inertia, by rearranging these two hand weights. So go ahead and hold your hand weights out. Okay. Side to side like this. Yeah, like that. Good. Okay. Now hold them like that. Hold them. Shalissa, hold. There you go. Then hold them. Now spin her up. Okay. And keep your feet up. Okay. Now she's spinning and she's doing a good job. Now bring those weights in. Did you see that? What did you see? She sped up. Her moment of inertia was smaller, so omega had to be bigger. How come I lost the... All right, let me see if I can. Hold on a second, you guys. Okay. Let me just get mic'd up again. Oh, that's right, yeah. Hand weights only. That's the fun one. That's the one where if you do it right, you can really, lose your equilibrium. All right, let's keep going here. All right, so getting back to these formulas, what you've just seen are some demonstrations of what happens when you rearrange R squared. That's the ice skater effect. And then what happens when you add up and interact with the angular momentum of the system by applying internal forces. Alex's muscle power. Okay, and actually, to the same extent, Shalissa exerted outward muscle pressure, but that didn't exert any torque, outward or inward. That didn't provide any change in the torque. But what Alex did, and so to conserve angular momentum, just like boxcars, when they interact, they'll have a new angular momentum, but it will conserve not angular momentum, the linear momentum. Same thing with these two spinnable systems. Now, make a note of it. In the Alex demonstration, it was two spinnable systems. First of all, the bicycle wheel can spin. on its axis. Second, Alex on the lab stool can spin about an axis that's vertical. You know, we can aim the axis of the bicycle wheel anywhere we want, and we can flip it. We can't really do that with the lab stool. But they're both spinnable, and we can use them to observe the exchange of angular momentum. And then the third one was gyroscopic stability. And this one, the bicycle wheel, we didn't get it spinning fast enough to really do a good job with gyroscopic stability, but you could see precession. All right. Now, we're going to change to a new topic. And this is all that I want to talk about for now about angular momentum. We'll keep talking about angular momentum from time to time. But for now, I want to talk about heat energy. And so this is in the next chapter. So we're past chapter 4. We're past chapter X now. And we're now into, I believe, chapter 5. Okay. This is a particularly famous image of the SUN, or images like this are famous. They're taken from space by a spacecraft called SOHO. This one is it's an ultraviolet image, and so it's not something that you could see with your eye, but they have ultraviolet cameras. And so what they do, they image the sun in ultraviolet, and then they do what they call false color. So wherever it's blue or even light blue or white is where you have the brightest ultraviolet coming from the atmosphere of the sun. And this is a part of the sun that is at 1 million Kelvin temperature. Now I'm going to explain that capital K there. That's for the Kelvin scale. We'll be explaining that in a minute. But here's the address where you can see this. It's the SOHO spacecraft. SOHO, www.nascom.nasa.gov. Just go there and you'll see all kinds of images. Not just this one, but other ultraviolet false color images. You'll see some visible images of this SUN. Some black and white versions of visible images. It's pretty cool. So we're going to be talking about heat energy. Let me ask you an easy question first. So using your eye clicker. And believe it or not, this is related to heat and temperature concepts. What is the average speed of this set of 4 molecules? We've got 4 molecules, so go ahead and compute. And this is something you can do on paper, so I'll give you a minute if you don't have your calculator. Thanks for helping me with that, you guys. Hector, did you get them all? Yeah. Okay. Now, can you see if you can attach those to a message in web courses to me? And try the smallest one first, and if it goes, yeah, don't do it right now. But, after class is fine. And, when you get a chance, and don't use up all your data plan. I mean, if you see if you can get on wireless or something first. Oh, okay. So here's what, okay, we'll probably dismiss early today, so we'll take a look. What, is that an Android or an iPhone? Okay. 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Woo. Almost everybody got it right. Um, Option B is correct on that. Now, just circle the concept of average speed and make a note of that because we're going to be talking indirectly about average speed today because we're going to be talking about gases and temperature. All right. The whole idea of molecules is related to something called the kinetic theory of gases. The kinetic theory of gases and the molecular view in general is not something that Aristotle would have bought into or thought about. Molecules were not something that we figured out until, I don't know, maybe the 1700s, late 1700s, early 1800s. And it was controversial up until the time of Einstein. You know, some people didn't believe in molecules and atoms. But Einstein showed that they were actually legit. A gas is considered to be a collection of molecules, and they're each far apart from the other, but there's a huge number of them. So they have to be really teeny. If they're far away, but there's a huge number, you know, like 10 to the 23rd power in an average, you know, so let's see, in one of those balloons that you buy at Publix, that, you know, a helium balloon that, you know, that's kind of shiny, and you give them to little kids for their birthday and stuff. That's going to have maybe on the order of 10 to the 22 or even 10 to the 23 molecules of helium inside of it. It's a huge number, small volume, and since the molecules are far away from each other at pretty much all times, uh, they, uh, they have to be pretty small. There's a random distribution of speeds, so there's some slow ones, some fast ones, and some medium ones. There's nothing that's at rest, and there's nothing that's going infinity miles per hour. But there's some really fast ones, not many of them though. And there's some really slow ones. They're just poking along, but not many. Most of them are kind of medium speed. And you can figure out an average speed. So make a note here with 1B, you can calculate an average. The problem is to do in the molecular view, to do the average with something where you have a huge distribution. In other words, you don't have just 4, you have 10 to the 22, you have to use statistical methods and a little bit of trig and quite a bit of calculus. So it's not something that we're going to do, but you can calculate it. Now these babies ricochet like BBs away from each other and from the walls of the container, but otherwise we consider it to have no interaction. So what that means is when you're up close, Celine, when they bounce off of each other, it's positive repelling positive. It's electromagnetic. The interaction is electromagnetic, but it's pretty much like they model it like little billiard balls. If you've ever played a game of pool, you know that the billiard balls they'll smack and then instantly go ricocheting off in some other direction. So that's how we kind of envision molecules. Now, if you model a single molecule interacting with one other molecule, then you would not model them as billiard balls. But on average, it's not a bad approximation. Okay. Same thing with the walls of the container. The wall is a set of atoms or molecules that are all interlocked together and rigid, and so they're not going to be floating around with the gas, but they'll still push back when one of the gas molecules hit it. Okay, and each of the molecules obeys, good old F equals ma, kinetic energy, 1/2 mv squared, all that stuff. In the kinetic theory of gas, however, one exception is made. And I guess you can make this 1e. We do not take into account gravitational interactions for the most part, because gravitational interaction is extremely weak compared to every other interaction. So we don't really think of, they actually are going on little arcs, but they're little parabolic arcs, but none of them go very far before they're on another parabolic arc. So it's basically a bunch of little ricochet and pretty straight paths, but different lengths, straight line segments, all in different directions, because we don't take into account the gravitational interactions. Now, the kinetic energy of the molecules in the gas, because they have a large random distribution of speed, there's a huge range from slow to fast. But the average kinetic energy is actually proportional to the absolute temperature. And that is why we began our first iClicker question of this day by asking you a question about average speed. Average speed is related to average kinetic energy. Right? So add up your kinetic energies and then divide by how many you have, and that'll be your average kinetic energy. That's pretty easy. The problem is there's so many of them you have to use statistical methods, so it's kind of tricky, and a little bit of calculus. But you can do it, and it turns out that the average kinetic energy is actually proportional to the absolute temperature. Now underline that term, absolute temperature. That's a concept for us that we're now going to explain in terms of the absolute temperature scale, or in other parlance, the Kelvin temperature scale. And here's a slide. I'm going to give you a slide of the Kelvin temperature scale. And actually, here's this ice age. What kind of animal is that, anyways? It's a squirrel? Oh, yeah, that's right, with an acorn. Okay. That little guy, he gets into so many scrapes. And then this is a thermal system over here. Anybody recognize where that is? It's not that far from here. Big, huge volcano. Where? It's the island of Montserrat down in the Caribbean. It's Soufriere Hills. Okay, here's a diagram that shows you the Kelvin scale compared to Fahrenheit and Celsius. Now over here on the left is Kelvin, and then in the middle is Celsius, and on the right is Fahrenheit. All right? And the whole thing about the Fahrenheit and Celsius, they're oriented to the boiling and freezing of water, H2O, at pretty much at sea level. I think in the metric system, it's the behavior of water in Paris, France, which is not sea level, but fairly close. Anyways, and then in the metric system, they say, all right, the temperature at which water freezes, we're going to call that 0, and then we're going to design our degree size so that 100 degrees away is where water boils. Okay, because metric system, they wanted to do everything in tens and powers of 10. So 100 degrees, 10 degrees would not be, it'd be too big, each degree. But 100 degrees between freezing and boiling, that's pretty good. So that's what they did. They're a little bit bigger than Fahrenheit. Fahrenheit uses 180. Oh, did I say 180 degrees? Yes. That is not a coincidence. That there's 180 degrees between boiling and freezing for water on the Fahrenheit scale. Now, this whole idea of absolute temperature, down here, the colder you go, one way to think of it is saying no random motions, your average kinetic energy goes to 0. Now, in the modern sense, we know that that is not correct because of quantum physics, which we're going to actually start talking about today in the context of thermodynamics. But it's a good way to think of the lowest possible temperature. Temperature is related to the average kinetic energy. So if you don't have if your average kinetic energy is 0, that means your temperature is 0. And that's how we define the Kelvin scale. It's the lowest possible temperature below which, I should say at which, any kind of fluid, either a gas or a liquid, will not be able to do any thermal work. In other words, you cannot run a heat engine like a steam engine in a locomotive or anything like that, or a steam. You know, all of our electrical generators, except for hydroelectric, they're all powered by heat. So they burn carbon, they burn coal, they burn oil, or they they don't burn, but they have uranium in the nuclear reactor that produces heat, a little bit of heat, just enough to boil water, and then that steam drives turbines and so on and so forth. Now, at this temperature down here, there's no turbine possible because this is the one that you can't get lower than that. You can only get a turbine to work if there's a differential in the temperature. So a cool temperature and a low temperature. The steam will go from a hot temperature to a low temperature. It'll expand and cool. And you can't do that. At some point, you cannot do that, and that's what they call absolute zero. And the Kelvin scale is oriented to using that. So let's take a look at some details about these temperature scales. And I'm going to forget about Fahrenheit. And by the way, if you hate converting between, raise your hand if you hate converting between Celsius and Fahrenheit. Okay. Oh, so most of you guys like to do it. So maybe I will have it as an optional bonus point question on the next test. Not. I see some guy in the middle over here going, oh, no, Dr. no. Yeah, we're never going to do conversions. That's stuff that's boring. And we're going to, and by the same token, we're not going to work with Celsius very much either. But let me talk about Celsius because it's kind of a cousin to the Kelvin scale. They're both metric system. Okay, so here's boiling of H2O up here, and that's considered to be 100 on the Celsius scale. Then freezing of H2O is considered to be 0 on the Celsius scale. And so 100 Celsius degrees in between them. Now, the Kelvin scale is also part of the metric system. So there's going to be 100 Kelvins up here between these two horizontal lines. But the lower end point of the Kelvin scale is going to be 0. All right? And, or as we say, that's your all stop. Okay? Now, by measurement in Celsius degrees, that all stop is at about negative 273 Celsius. I think it's like negative 273.15 or something like that. Okay? You can look that up. But negative 273 is good enough for government work. And that's what we're going to do. And so on the Kelvin scale, every Kelvin is the same size as a Celsius degree. All right, so up here, you're going to go 100 Kelvins between these two parallel lines up here. And so the basic rule is to go from Celsius to Kelvin, almost said Kevin McAllister, Home Alone, Kevin. So Celsius to Kelvin, just add 273. All right, that's pretty good. Now, most of the time, I'm going to give you Kelvin and only Kelvin, so you won't have to worry about this. But you should know a little bit about it. And here's an example. H2O, the freezing point. Celsius, it's 0. Kelvin, it's 273 Kelvin. Just add 273. Ding. You're good. So that's not as pesky as, like to convert from Fahrenheit to Celsius, you have to multiply by 5/9 and subtract 32 or add 32 or multiply by 9/5. It's a menace to society is what it is. And so I try to avoid that junk. Okay, so here's your 273 up here on the Kelvin scale. And then by the same token, boiling point is 373. All right, so here's 100 kelvins between those 2 points over here on the lavender colored scale on the far right. All right, and by the same token, this is 0 Kelvin down here at the very bottom. All right, now let me pause for questions. 1 or 2. Yes. The question is, the molecules are far apart, they're flying around, there's nothing in between them. What is there between them? What is that? It's the vacuum. It really is nothing. Their state of motion. You know, they zip around. It's kind of like a a pool table, and you break, and those, all the billiard balls, they go all over the place, right? But there's a little bit of friction, so eventually they slow down and stop. So if the idealized kinetic theory of gas is like that, except no friction. They're just going to keep zipping around, and so it goes from a solid to a liquid to a gas, and once it goes from a liquid to a gas, they're loose. It's like breaking in a game of pool, but there's no friction, so they just keep zipping around. Unless you cool them down, then you can condense it from a gas to a liquid, and then cool it down some more. You can freeze it. We're going to talk about that on Tuesday. So, but yeah, it's a vacuum. It makes you really wonder, what is solidity? Because it boggles the mind. So let's do a few follow-up questions on temperature. Question number 2 for today. I might ask you 1 Kelvin to Celsius to Kelvin question on an exam or homework, but not more than that. And for those of you that don't have a calculator today, this should be sufficient. Just add them together. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Ding. Actually, a couple of you voted 120. What is negative 129? Is that 144 minus 273? Okay, so that's no good. 112, 144. Yeah, so the only one that's bigger. So here's a little secret side note. Taking Dr. B's test. A lot of times you'll be able to figure out there's only one answer that's possible if you know that you have to add to the Celsius. The only thing that's lower than 144 or bigger than 144 is 417. So that's the only possible answer. Okay, and there's your calculation. All right, now let's make a list of a few other everyday temperatures. Room temperature, usually considered to be 290. 290 Kelvin. And what we're going to be doing in the next week or so are some difficult brain burners involving heating and freezing of water and other things. We'll always be working in Kelvin, frequently near room temperature. So 290 is a good number to remember. Human body is about 310, 98.6 Fahrenheit. It's about 310. Standard temperature and pressure, 273 Kelvin. That's something that the chemistry department talks about all the time. You know, doing a chemical reaction at some standard, and it happens to be 273 Kelvin, freezing point of water. Mount Everest on a cold night, top of Mount Everest, 238 Kelvin. So if you're below 273, you're starting to freeze your you-know-what off. And 238 Kelvin, you've definitely risked freezing your you-know-what off. All right, so just go ahead and jot some of these down. And we're going to be working with, you know, melting copper. You have to get copper pretty hot. Melting gold, you got to get it pretty hot. And we'll work with the Kelvin temperatures of those things. When we melt something, we're going to melt it at a certain Kelvin temperature. And oh, by the way, on exam 3, if you have some calculations to do involving temperature, melting points, stuff like that, I'll put that on the cover page. All right, so you won't have to worry about memorizing it. You just got to remember how to organize and execute with it. Okay, we're not done. We're still going, man. We got a bunch of slides here. I don't know what you guys are doing. I have a question. First of all, can Dr. B spell? No. Second of all, how smart is your nose? All right, here's your question. "20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Release the Kraken. Actually, F is not possible. You can't vote for it. But hopefully you voted for this. Let's see what you guys voted for. Uh-oh. Yeah, ammonia is pretty pungent. And I want to talk about, here's the chemical formula, NH3, for ammonia. Now, if you're in a, here's a kind of an interesting fact. If you're in a room and you open up a big bottle of ammonia, its smell will eventually permeate through the room. All right. Now, it happens faster if the room is hot than if it's cold. Now, you may not go around doing nose tests, temperature for temperature, but apparently there are guys that have, and they've noticed that this is true for ammonia. And this is an example of the average kinetic energy being correlated to temperature. So if when you release those ammonia molecules, they're going to equilibrate with the room temperature. Therefore, they're going to have a certain average kinetic energy. That means that on average, if you have a lower average temperature, you have a lower kinetic energy, they won't get across the room as fast as if the temperature is hot. There are zillions of molecules in a room, and those motions are random. And you can think of it as having, of the gas as having a zillion different kinetic energy states. Now, even though there's a zillion different kinetic energy states, zillions of teeny tiny molecules, there's only one average. You can always, if you know the temperature, you can calculate the average. And as I mentioned, the average kinetic energy is proportional to whatever the Kelvin temperature is. So in other words, the kinetic energy average is a number times the Kelvin temperature. Okay, so if your gas is at 400 Kelvin, just take 400 times, and there's this constant called the Boltzmann constant that you use. We're not going to calculate with that, but you can do it. And this is the concept, that it's proportional to the Kelvin temperature, the kinetic energy average. And that's per molecule. Now, I want to discuss another thermodynamic concept. And to do that, we'll start talking about this guy, Max Planck. Go ahead and write down his name. It's pretty important for us. Planck, Planck, German physicist. And he was a theoretical physicist in Kiel, Germany, and then in Berlin. And in the 1890s, he was studying thermal physics in detail. And one of the problems that they had at that time was figuring out the entire spectrum of electromagnetic radiation and how that varied with the temperature of an object. For instance, if you've ever seen a cast iron stove that you've put a lot of wood in and it's really burning hot, sometimes you'll see it get red hot. The burners on your electrical stove, when they're at high temperature, they're red hot. Now that whole idea of the color of something correlating to its temperature is related to the fact that when you heat something up, it'll emit electromagnetic radiation all across the spectrum, from infrared all the way up to visible light and all the way up through ultraviolet, possibly even X-ray. Now the human body at about 310 Kelvin radiates mostly infrared. Make a note of that. Human body mostly emits infrared, and that is why at night you cannot see a person with visible eyeballs, but if you put on your infrared night vision equipment, you can see somebody in infrared. And it's very dramatic, especially in a place like the desert where the rocks and everything, the surface cools down really rapidly, and so you have a very cool background and a very hot human being, because humans stay at 98.6. So we're always emitting in infrared. You just can't see it with your visual eyeballs. Now, there's a theoretical object called a black body that he was studying. And hypothetically or theoretically, a black body is an object that's a perfect absorber and a perfect emitter of radiation. Okay, and that was a black body alarm going off over there somewhere. Okay, so a black body is this kind of theoretical, idealized object. You know, like a molecule is idealized as a billiard ball. And, the human body is not a perfect emitter or absorber. The sun is not a perfect emitter or absorber. But they're fairly close to that. And one of the things that they noticed was that they couldn't really predict theoretically how much radiation at which wavelength would come off of an object according to its temperature. The way that they did that, and I've done this in the lab myself, you take you take heating elements like that are in your stove, and you take 6 of them, and you make a little cubical furnace, so the top and bottom, all 4 sides, are heating up, and you just set them all to the same temperature, and then the radiation coming out of there, it might be red hot, or if it's even hotter than that, it'll be yellow, or blue hot, or white hot. That's when you get all the colors in there. And you can, rev up certain things to really high temperatures and then measure the radiation. Nobody could figure it out. until Max Planck. In 1900, he wrote a theory of black body radiation and introduced the quantum of energy and his quantum constant, which is symbolized h, lowercase h. That is called Planck's constant. And he didn't know it at the time, but this decision that he made to orient his theory to the energy of oscillators coming in bundles of energy proportional to this constant it explained black body radiation perfectly, and it actually started the quantum science revolution. So let's take a look at some spectra of black bodies. Here are 5 different black body spectra. See if you can jot these down and make a diagram with them. The first one is an object that's at 5,500 Kelvin. The next one is green, it's 5,000 Kelvin. The next one down, the third one, the middle one, is 4,500 Kelvin. And then the 2 lower ones are 4,000 and 3,500 Kelvin. Now the vertical scale is how bright the object is. And they've segregated it into wavelengths. So that for the 5,500 Kelvin object, it's really bright down here at about 500. And for the 3,500, its brightest, its max brightness is down here. I don't know, what about 800, 900? Down here, this one. So these peak values in the brightness, and down here, these are longer wavelengths. By the way, a nanometer, nm, is the wavelength of light, and that's a billionth of a meter. Anyways, nobody could predict these curves. They could measure them, but nobody could understand and explain, well, this is why nature does it. But the guy, and here's visible light. Visible light is from approximately go ahead and make a note of this, 400 nanometers to 700 nanometers on this. So you can see that this big one at 5,500 has got a lot of brightness in the visible. And then this one down here at the bottom, 3,500, it's got most of its brightness at longer wavelengths. Those are infrared wavelengths. The cooler the temperature, the shorter the curve, it's not as tall, and the peak shifts into longer wavelengths, which are infrared. Now, students, these spectra are what we observe for many, many stars. These temperatures represent the surface temperature of many stars. So these are kind of spectra that we find all the time in real life. And our main point is that only H could render the shape of these spectra comprehensible. Okay, it's 11:50. Homework 12, look for that by lunchtime tomorrow. You're dismissed. I'll see you next week.